This is a lesson on exponential and logarithmic properties in algebra in a precalculus course. This may be a review to you. I am definitely doing a pretty thorough lesson on how to use what is exponentials, what are logarithms, how do they relate, and what are the properties and rules that we use for algebra that make them useful. They can seem, I think, intimidating at first for students, but when we see what they do and understand what they do, they're one of the more useful functions. I mean, you're learning them in precalculus along with the toolkit functions. They're one of the most useful functions. So exponentials, I want to talk about what exponentials are because I see students use the word exponential incorrectly all too frequently. An exponential is an expression with the unknown or input variable in the exponent. All right, that's why it's called an exponential, because that x is up in that exponent. An exponential is not x raised to a power. All right, so we've looked at polynomials before, x squared, x cubed, all of those, x raised to a power. I know that you think that there's something to do with the exponent there, but when we're talking about exponential, we're talking about where that unknown or that input variable goes, and that goes up in the exponent for exponentials. I brought out the curves here too. I see students look at graphs and say, oh, the graph is shaped like an exponential, when really what they mean is a power function. So when I look at this graph, this red line here, you may recognize this red line. This red line here is x squared. That is a parabola. It's symmetric around the y-axis. This blue line on my graph is 2 to the x power. Do you see those? It's x squared and 2 to the x. They're both the same like number and letter, but they look different. They definitely look different and behave different. It turns out when you raise a number to x, it starts growing at a much, much faster rate than raising a number to a constant value grows. All right. This little green one down here, I don't even know if you can see that down there. This is the log base 2 of x, and you can see a logarithmic function acts differently on a graph than the exponential function and the polynomial function, even polynomial here that I have. All right, so I wanted to show those graphs and give you a really strict mathematical, technical definition of what an exponential is and what I mean by an exponential, what people mean by an exponential. So here's the question, like, why do we use logs? And I mentioned this before. We need a mathematical tool, and what this does is help algebraically solve for bases and powers. We can see this. I'm going to erase. That's why I have my eraser up here. We can see up here that we have x in the exponent. And there are no normal sort of algebraic things that we can do to solve for that x up in the exponent. It turns out when I have the unknown in that exponent, I have to use a very specific algebraic technique with logs in order to isolate that exponent. So what's the definition of a log? I have this here. When I define the definition of a log base b of y equals x, and then we're going to say that's equivalent to, there's an equivalency here. These two expressions are the same. This log expression is equivalent to y equals some base to the x power. Okay, so that's what we mean by it. It is a little heuristic and algorithmic that you have to remember what that is. Okay, if I have a number raised to an variable in x power, all right, I can represent that expression as a log expression. B is the base of the log. You can see that down here. We put it down here. It's at the base of the log. It's the base of the log. It's also the base here, this base number. Right? So it's the foundation from which we watch this exponential grow. It's always a number, and it's related to the scale. We can have base 2, base 10, base 50, there's all sorts of bases that we can have. X is the power that the base is raised to, and y is the result. So we can see that over in the equation here, y equals b to the x power, and we can rewrite it as a log expression in these terms. Okay. The log in your calculator is a log base 10. Like if you look on a scientific calculator, it just says log. It is implied. It's not written on there, but it is implied that it's a log base 10. And a log base 10 is a very common and actually useful base. Logs can have any number base, but some are more useful than others. I mentioned that with 2 and 10. So what I wanted to do is look at this definition and apply it a little bit. I have a couple of examples here I had under that graph. So I have this expression here and we want to simplify it. Log base 5 of y equals 4. So what we're going to notice is that we have the expression in terms of this, right? That's what the expression looks like, that blue. Log to a base. We can see our base is 5. We have some unknown value that we don't know. We're trying to solve for it. And that equals x. Okay, so I am going to transfer this to the other form, this exponential form here. All right. The blue is the logarithmic form and the pink is the exponential form. So if I transfer this expression to exponential form, I'm going to put each one of those things where they go. Let's see, y is an unknown thing. I don't know why. Next comes the base. I'm going to notice in my expression, my logarithmic expression, the base is 5. And then the x value is on the other side. This is to the 4th power. Y equals 5 to the 4th power. Well, I know 5 squared. I have a 5 squared times a 5 squared. 25 times 25 is 625. Okay, so when I solve for y, I actually get a number, and that's the relationship among those. Okay. Down here, I have a log base 10 of c equals negative 6. We can do the same game, but I put a negative in here. I'm going to remind you that we can have a negative in a certain place, all right? Notice that we have c here. We don't know c. We're going to take 10 to the negative 6th power. I can rewrite this as 1 times 10 to the negative 6th power, or any number is 1 multiplied it by itself, right? So I'm going to notice this maybe as a chemist or a physicist that this is like a micro. You might be working with pHs and concentrations, etc. All right, so you can see how that base 10 works as well. I wanted to go back and talk up about this stuff here. So there may be situations where you can solve for x pretty easy while it's up in the exponent, right? 2 to the x power equals 4. Okay, that's not too hard. X equals squared, right? You square 2 and you get 4. X 2 to the what power equals 16? Well, 16 is 4 times 4, so that's 2 squared times 2 squared. So that's 2 to the 4th power, so x equals 4 in this situation. Pretty, not too like completely easy, but it makes sense, right? If I take 2 and raise it to the 4th power, that gives me 16. We're going to be able to solve more complicated equations here. 2 to what power equals 92? Well, 92 is not a perfect multiple of 2. There's no integer value of x that we can put up here that would result in 92. So we're going to assume that that's 2 to some number value with a decimal behind it. I don't know what it is. What we're going to do is we're going to learn how to solve that equation. We're going to learn how to solve 3 to what power equals 4. Right? There has to be 3 raised to some power that equals, just happens to exactly equal 4, and we can figure that x out. So that's the power of logs, is that they're going to allow us to access this unknown variable in exponents that we might not have otherwise been able to isolate. I have an example here to get to that, all right? It says solve for x using the definition of the logarithm. So we were just looking at the definition of a logarithm. Log base b of y equals x, and that is an equivalent expression to y equals b to the x. Well, we're going to notice that we have this expression here. It's a logarithmic expression. So what I'm going to do is I'm going to note b, y, and x, and I'm going to put them in this form. And you'll see how I'll be able to solve for x from there. All right, so the base is 2. I can see that, right? B, the base is 2. So let's see. Also, y is 7x plus 5. So I'm going to say y equals b to the x. So y is 7x plus 5. My b, my base, is 2. And then the x value here is 5. All right, it's on the other side, and that's what the base gets raised to, is the 5th power. So you may recognize right away that I have a linear equation now that I can solve. To the 5th power, do you know 2 to the 5th power? 2 to the 5th power is 32. I'm going to subtract 5 on both sides to isolate the 7x, so I get 27, and I get x equals 27 over 7, and that will be my answer. So that's how you apply the definition in order to solve for an unknown variable. The next thing I wanted to remind you of is logarithms of base e. This is the natural logarithm, all right, the natural log. E is just a number. The number e is a mathematical constant. To me, it's similar to pi. It is a number. It's an irrational number. Remember, irrational numbers can't be represented like just as a fraction, right? That's a ratio. That would be a rational number. This is an irrational number. There's no two integers that I can put over themselves that will equal this. But it does have a value. E is equal to 2.71828 blah, 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 blah. It keeps going on and on and on. And I'm just going to say there's a button on your calculator for it. It'll say e raised to, and you're going to have to put an exponent up. Okay. So the natural logarithm is what we're going to define as a log base e. It's the same log as before on the prior slide, except now that I have it as a base e, which is a kind of weird thing, except this is a magical number in nature. This is what similar like a golden ratio sort of situation where there are a lot of natural occurrences, natural phenomena that have e as a natural base for their growth or decay. So we do not represent it as a log base e. We represent it with an ln. Okay, so to me that stands for log natural. A natural log natural. It's a natural number, so we get a natural log out of it. The last thing I'm going to note down here is that any base to the x power can be represented as e to the k power to the x. I'm going to say that any number can be e raised to some number. Any number can be e raised to a number. I think that's pretty true. Like I can say 2 is e to some number. If we're looking at a situation where we want a nice exponential with e as the base, then we can transfer from any old base to e to a power to the x power. Okay, so let's look at an example for natural logarithms. I wanted to just lead you through a few of these to get you used to these. This says, write the exponential equation in logarithmic form. So we're going to note that this is an exponent equation, and they want it in logarithmic form. So I have to take the base and the y and the x and put it in the right places in the logarithmic form. I'm going to rewrite this e to 1 over e to the 4th power. I'm going to rewrite that as e to the negative 4th power. Do you all see how that reciprocal, it just like when you invert it, you get the negative sign? So I'm going to take those two things. I'm going to see that this is b raised to the x power, and I'm going to see this is y. So I'm going to set up the logarithmic equation. Okay, log base b of y equals x. I just remember it. I think you'll want to put some effort into just remembering it. So I'm going to line up the b's and the b and the x and the y. I just put them in the right spots in this equation. Just put them in there. So I have the log base b. I'm going to notice my base here is an e base. Y is from the other side, 0.0183, and that has to equal x, which is negative 4. Okay, I don't prefer this form, log base e. We do not keep a log base e. When I see I have a log base e, I'm going to transfer it to a natural log. So this expression changes into logarithmic form. Natural log 0.0183 equals negative 4, and that's going to be the answer for that part. Let's do part B here. B says write the logarithmic equation in exponential form. It's sort of the opposite of what we just did. We're given this equation, so then what does it mean it started out as, right? I'm going to remember a natural log is a log base e, and I'm just going to kind of rewrite this so that my base is more apparent with the natural log. There's my base b. That's b, this is y, and this is x. Notice right away I go through and identify b, y, and x. So I'm going to take y equals b to the x power. Y is 0.1353. My base is e, and x is -2. All right, so that's it in its exponential form, transfer from the logarithmic. So you'll see some of these problems just having you practice transferring between these two equivalent forms, these two equivalent expressions. So they will be useful. I think there's going to be some situations where they're useful, and you'll see that in a little while. A couple of properties I wanted to go over here, logarithmic properties and identities. One of the important things, and as we think about logarithmic functions and exponential functions, I think logarithmic functions in particular, is that negative numbers DNE. If you cannot take the log of a negative number, why is that? Let's go back to the definition. Remember, I have a log base b of y equals x. So when I transfer forms, when I go back to the exponential form, that's saying y equals b to the x power. So in this situation, we have a base 10, and we have some unknown exponent, and we want y to equal -3. And what this equation is asking me, what I interpret that is asking me is 10 raised to what power equals a -3? And I am telling you this does not logically parse. There is no exponent that you can raise 10 to in order to get any negative number out. It's not so much the 3 part, it's that there's a negative out front here. There's no exponent. So I have students say, well, what about like to the negative, I don't know, something, right? -3rd. Remember, when I take a number to a negative exponent, I get 1/10 cubed. There's no negative out front. A negative in the exponent does not cause a negative out front. And so that is why this is not true. Why 10 log negative any number does not exist is because there's no number you can raise a base to get a negative number out. So we cannot evaluate the log of a negative number. We're always going to have some like domain restriction that x has to be greater than or equal a number or less than or equal a number. You're always going to have a domain restriction. So keep that, we'll keep that in mind as we move forward to exponential and logarithmic functions. Another thing we have going on here, I think, is maybe, I don't know, it's trivial, it's obvious and trivial, like you wouldn't think about it, but I'm going to say it aloud anyway. Log b of 1 equals 0. So what this is asking is a base to the 0th power, right? This is the base, and then this is x, equals 1. We already know that. 2 to the 0th power is 1. 10 to the 0th power is 1. 50 to the 0th power is 1. Any number to the 0th power is 1. And that's what this is saying. The last property here I wanted to go over is the one-to-one property. Again, I think this is pretty like a trivial one, but sometimes it's a useful thing to remember in problem solving, or to get arrange things in a way that you can set m and n equal to each other and not have to deal with logs overall. If log base b of m equals log base b of n, then let's just deal with m and n and not the logs part, if that makes sense. Okay. One of the properties I'm really going to highlight for you here in this lecture is the inverse property. And this is why logs were invented. We had an expression, y equals b to the x power, and we couldn't solve for x. So if we take the log of different ways, we're able to solve for x. We can solve for x with a log. That's why logs were invented. Okay, so how do we use this in order to do some algebra? I think that's the question here. So the inverse function, and we're remembering what inverses do, right? We're most of the way through a pre-calculus course. We've been covering inverses for a while here. An inverse function undoes the original function. If I have b to the x power and I apply its inverse to it, I'm going to get the input out, right? Whatever was the input for one is the output for the other. To me, this is the equivalent, like if I have the square root of x, in order to get x out, I have to square it. If I have a number raised to an exponent and I want to isolate that exponent, I'm going to take a log of that base, the same base. That's how I'm going to undo that exponent and isolate x out of there. So, such as log base 10 of 10. Remember, 10 is 10 to the first power, so that's how we get 1. Log base 10 squared is 2, right? We're going to take the log base. As long as those two things match, what we get out is that exponent. Okay, so I have a couple, I'm going to note this. I'm going to highlight it. This is, to me, I went through all these properties and I realized it's the #1 most frequently used property in algebra strategies. I will show you a few examples. Let's just practice using the law. I just want to practice using this property here. Let me get rid of this. I don't want that down here when I solve that second example. Log base 7 of 7 to the 13th power, what is x? Well, I'm going to say that this base and taking log of that base undo each other, and we're just going to get x equals 13. Done. That's it. That is it. That's the elegance of using the same base log. Log base 2 of 256. This looks like you can't really do anything here. It's not like 2 raised to the 56th power. It's like 256. If you're in computer science or you know anything about powers of 2, you're gonna, or you could just do prime numbers, right? You can just do a prime factorization too. If I take 256 and divide by 2, I get 128. I can take 128 and divide by 2, I get 2 times 64. I can take 64 and divide by 2. I get 2 and 32. I already worked with 32. 32 is 2 to the 5th power. So when I add all of those factors of 2 up, I have 1, 2, 3 plus 5. This is 2 to the 8th power. So if I take the log base 2 of 2 to the 8th power, did you see how I changed that around? So now I have 2 as the base of my log and the base of my exponent. When I take log base 2 of 2, I'm just going to get that exponent back out, and that is 8. So that's a really, really nice property, super nice property. Let's use it here on this example, the inverse property, and this is take 1. We're going to solve the same problem twice, but I like how this is solved with the inverse property. So it says solve the equation for t. I'm going to note that my base is 2. So if I want to use the inverse property to solve, I'm going to take a log base 2 in order to get rid of the 2. So that'll do it on this side. But remember, whatever I do on one side, I have to do on the other side, which means that I'm going to do a log base 2 of 42 as well. Okay, we're not multiplying by log base 2. We are taking the log base 2 of 42. It's same like if I have x squared equals 42. If I do a square root on this side, I have to do the square root on this side. I'm operating on 42. That's how we think about it. So let's keep solving this equation here. I'm going to note when I take a log base 2 of 2, that's going to cancel each other out. Over on this side, I'm left with just that exponent. -4 over t. Over on this other side, I'm going to have a log base 2 of 42. And if your calculator is fancy enough, you can do a log base 2 of 42 in your calculator. I'm going to do one more step and solve for t. T equals -4 log 2, -4 over log 2 of 42. So when I solve t, and you can plug this into your calculator, what I did, my friends, is I plugged this into Desmos. You can see the Desmos answer here. Desmos lets you do a log with a base. You just do an underscore, and you can access that. You can program it into, I think, down in the keyboard setting. So that's how I did that. They told me that log base 2 of 42 is this number, so I'm going to take -4 and divide by this number, 5.39232. I'll just end it there. And when you calculate this value, I have it over here, you get negative. It's a negative value because there's a negative up in that numerator there, negative 0.741796. I mean, you could round it to like 3 or 4 decimals here, but that's the answer. You get an answer. It's a number. Okay, so that's how you use that inverse property. Whatever base you see, you do log of that base on both sides, and then you can solve. Okay, so you're seeing that this is one of the more, like, the most powerful algebraic technique to be able to isolate for a variable in an exponent is to use the inverse property and take a log base of whatever that base is. So we're going to keep that in mind for our algebra. The second most popular, most frequently used property in algebra involving logs is the power rule. There's some power to the power rule. We're going to rewrite the log of a power as the product of the exponent and the log of its base. All right, so that was a lot of words that I think are represented better with just looking at this equation. I have a log base b of something raised to a power. And so what happens, what we can do is take whatever that power is up here, whatever that exponent is, we're going to move it out front. That's how I think about it. We just move it out front. Do you see how it's just out front there? A lot of times you'll see it used in conjunction with the inverse property. Let's do this little example here real quick that I wanted to show you. Let's do a common technique. This is a pretty common technique. It's a really great tool. If I have something up in the exponent, I want to solve for it, I'll just take a log on both sides. And I'm going to remind you that if I take just a regular log in your calculator is a base 10, I'm not going to write 10 down there for the base. I'm just going to remember a normal log on the calculator is a base 10. It turns out you can do this calculation with any log of base, but what we're going to do is we're just going to use a log base 10. And what that does is when we do this, we're going to use the power rule. Do you all see how we can use the power rule now? Now that I have a log on both sides, all right, I can bring that out front. So let me rewrite this. I'm going to have a log base 10 of 4 to the 3x plus 5 equals the log base 10 of 44. This is a number I can calculate in my calculator, just log 44, and I get a number. I'm going to use the power rule to bring this out front. Do you see I can bring this out front? So I get 3x plus 5 log 4 equals log 44. Okay, I'm isolating x. I'm going to divide by a log 4 on both sides. Log 4. So some algebra notes here. An algebra note here. When I do this, I'm going to get 3x plus 5 on this side. Log 44 over log 4 does not simplify to 4. Those logs do not cancel or anything like that. That's it, like saying the square root of 7 over the square root of 27. You don't get the square root of 2. It doesn't simplify that nicely. The square root of 7 is a number. The square root of 27 is a number. In this situation with the logs, I have to calculate log 44 as its own number and divide by log 4 as its own number. I'm still isolating for x. I'm going to do a couple of steps here. I'm going to subtract 5 on both sides. That's going to get rid of this 5 on this side, and then I'm going to divide everything by 3. So this simplified, I mean, it's not simple, but the simplest form of this, I'm going to say is, maybe I'll just bring that 1/3 out front. 1/3 log 44 over log 4 minus 5. And then that is what x equals. You would be able to calculate it as a decimal. I would calculate it. I would get my calculator out and plug those things into my calculator and calculate it as a number. I don't know what number it is, but it's a number. Okay, so that is an example of how you're going to be using logarithms a lot. The inverse property is a very nice property. You're going to be using the inverse property when you have a base you recognize. If you have some just like any old base, base 4, base 52, base 126, who knows, right? Any old base, I would just get a common log out, just a common log base 10 out, take a log on both sides, and then that lets you bring this exponent out front and solve for that exponent. So simple. Okay, once you know what you're doing. Let's do this again then. Solve the equation for t. We already did this problem, but we're going to use the power rule now rather than the inverse rule. So instead of taking a log base 2 like we did before, I'm just going to take a regular log on both sides. So I'm going to get a log base 10, right? A log base 10 of 2 to the negative 4 over t equals log of 42. All right, now I can bring this exponent out front and have the log 2 there. So I have negative 4 over t times log 2 equals log 42. So negative 4 over t equals log 42 over log 2. I can solve for t in this situation. I'm still going to get a negative. I'm going to flip it and move it around. Negative 4, oh, I already have a negative. 4 log 2 over log 42. And then I would plug that into my calculator. I looked this up. I had Desmos. So if I just do a regular log, those are the regular logs in here. In Desmos, negative 4. You can see log 2, 0.30103. I'll just leave it like that. Log 42, 1.62325. And then you would just divide those, and you would get a number. I'm not sure what that number is. I didn't solve it before, but it's just a number that you can calculate in your calculator. Now you can solve what is that value t that makes that expression accurate. Let's look at this next example. I had mentioned earlier that you can write e to some number has to equal a base. Sometimes, a lot of times, you'll raise that base to a power. But in this situation, I just wanted to explore this relationship. E written to some number has to equal a base, okay? So we looked at this example a little bit earlier. We know e to the negative 4th power equals that value. You can plug it into your calculator. It's kind of trivial. But what the problem's asking us to do is say that 2 to what power equals this? 0.01383, okay? And I think more specifically, what I want you to realize here is that e to the negative 4th power equals 2 to some power. So what I'm going to do is I'm going to use my inverse property. Let's use an inverse property, and it'll give us a power property as well. I'm going to note that I have a base e, and when I have a base e, if I take a natural log, and I'll take a natural log on both sides because I have to take a natural log. If I do it on one side, I have to do it on the other. When I take the natural log of base e, those kind of cancel each other out, and I'm left with the exponent here. That's the inverse property. So that's the inverse property. On the other side here, I'm going to take the natural log of 2 to the x power, and I'm going to apply the power rule. The power rule here for exponents says that x2 times natural log 2. Instead of 2 to the x power, I'm going to get x times natural log 2. So I know x equals negative 4 over natural log 2. I can say this is true. E to the negative 4th power is 2 to the negative 4th divided by natural log 2 power. Kind of interesting. It's true, you can do that with any number. It says up here, and base 10. I could play the same game where I say over on this side, instead of having a 2 here, I could have a 10 here. 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 E to the negative 4th power is 10 raised to the negative 4 natural log 10. It could be any base down there. Like I said, you could do 235. You could do any base there you can transfer between. Or you could take any base and make it exponential. Sometimes that's convenient. I like doing that, especially if like I have a continual growth or a continual decay, and that happens a lot of times in STEM. Newton's law of cooling is an exponential. Radioactivity can be modeled as an exponential. Population growth can be modeled as an exponential. There's a lot of situations where instead of having a base to some power, I would rather have e to some power because it represents a constant growth or decay. Okay, so that's the trick that I'm really trying to drive home here on this side. Hopefully you'll find it useful sometime in your future. A few last properties here that I want to go over is the product rule and the quotient rule. You may have seen these before if you've done log stuff. If I have two things multiplied together, instead of like something to a power, these are just multiplied together, and you take the log of it, you can divide it up with a plus sign. So c times d, the log base b of c times d equals the log base b of c plus the log base b of d. And if you have a division there, c divided by d, you're just going to have a minus sign in the middle rather than a plus. I'm not going to go through the properties that make that true. I will say here that this allows us to expand logarithmic expressions with a complex input. So that's the example I have up here. We can expand. Log 7c over 6. I can say this is log 7 plus log c minus log 6. Right? 7 times c is a product, so I'm going to use a plus sign. I have a division sign in here, and that division sign corresponds to a minus sign. The other benefit that we get from these sort of properties with the product and quotient rule is we can condense logarithmic expressions and make them easier. So you're going to see that in this example here, I have a quadratic over a quadratic. Right? This is a negative sign in here, so I have a division situation going on because of that minus sign. I'll have the log 2x squared plus 3x plus 1 divided by 5x squared plus 6x plus 1. You may already see that you can factor these. This is going to simplify a little bit more. We're going to have a 2x plus 1 on top times an x plus 1. On the bottom, we're going to have something similar, 5x plus 1 times x plus 1. And when we simplify this overall, we're just going to get a common log base 10 of 2x plus 1 over 5x plus 1. There's no more simplification you can do there. Don't go making up your own algebra rules where you simplify too much, all right? That's it. We have this expression over this expression. And so it takes something more complicated and we have something a little bit more elegant and packaged into one expression rather than a bunch of stuff going on. So watch out for those properties. You can use those to simplify. The last thing I want to go through here is a change of base formula. I like a change of base formula, especially if I only have like a scientific calculator nearby that has a log base 10. Notice my example here, I have a log base 15. If you have a fancy calculator like Desmos, you can put it in there and you can use a log base 15. But if you have just a regular calculator, or you're doing computer coding and just want to use a regular log. If I have a log base b of any base there of a number, we're going to take a new log of a different base. Right? You're going to have a different base here, but it has to be the same base on top and bottom of the result over the old base. Okay, so that was a lot of jumbled words maybe. So if I take log 15 over 86, if I just do a log base 10, a common log, a log base 10, which is just log, right? Log 15 over 86 is going to be a log 86 over log 15. I'm just going to transfer it to a new base. So that's why we call it a change of base formula, is I change this base from 15, now I have a base 10. That's the one I have in my calculator, so that's convenient. And to double check, I got this out in Desmos. Desmos is fancy enough that I can put a log base 15 in it. You can see the log base 15 at 86, 1.6 and some stuff. If I take the common log of 86 over the common log of 15, I get that same dang number back. You can see that they're equivalent. So that's what that expresses. It can be convenient sometime to do it. And get ready to take a screenshot. I compiled all of these rules and properties together into one slide so that you can reference it, or you may want to just write it out in your notes. A screenshot or a picture works as well so that you'll have them for when you're solving equations as we move forward in the exponential and in the logarithmic functions sections.